Good evening. Myself, G. Rutvik. I'm from CSE C section. My ID number is 21951A05G2. Today we are going to see linear algebra and calculus. My topic is a continuation method for emission tomography. One approach to improve reconstruction in emission tomography has been the incorporation of additional source information via Gibbs prayers that assumes a source F that is piecewise smooth. A natural Gibbs prayer for expressing such constraints is an energy function E defined on binary valued line processes I as well as F map estimation leads to difficult problem of minimizing a mixed variable objective function. Previous approaches have used Gibbs potential functions phi f sub v and pi f sub h defined solely on spatial derivatives f sub v and f sub h on the source. These pi functions implicitly incorporate line processes, but only in an approximate manner. The correct pi function pi sub consistent with the use of line processes leads to difficult minimization problems. In this work, the authors present a method wherein the correct pi sub function is approached through a sequence of smooth functions. This is the essence of a continuation method in which the minimum of the energy function corresponding to one member of the pi function sequence is used as an initial condition for the minimization of the next less approximate stage. The continuation method is implemented using a GEMICM procedure. Simulation results shows improvement using the continuation method relative to using pi sub alone and to conventional EM reconstructions. Can maths really save our life? Of course, it can. Maths has applications to many problems that are vital to human health and happiness. The in this, we are going to describe how the mathematics of tomography has become one of the most important applications of mathematics to the problems of keeping you alive. Modern medicine relies heavily on imaging methods, starting with the early use of X-rays at the start of 20th century. Essentially, these imaging methods take two forms: X-ray and ultrasound methods. Use a source of radiation that lies outside the body. The radiation is detected after it has passed through the body and image constructed from the way it has been absorbed. When X-rays are used, this process is called computerized axial tomography. Milk delivers and killer Sudoku is an example. Before delivering into the depths of medical science, we will start with a simple example which illustrates the principles of tomography and which has a very nice link to various types of Sudoku that have become very popular recently. This example involves milk deliveries. Imagine that milk and fruit juice is delivered in a bottle that are placed in trays with 9 compartments arranged as a 3 into 3 grid, which each compartment of the tray contains a bottle which may contain milk, juice, or be empty. The question is which type of bottle is in which compartment. Unfortunately, other trays are above and beneath the one we are interested in, so we can't look down on top of the tray. At first sight, it will seems impossible to solve this problem. However, we can peer in through the sides and we can measure how much light is absorbed in different directions. Different type of bottles absorb different amounts of light. Carefully, measurements have shown that milk bottles absorb 3 units, juice bottles absorb 2 units, and empty bottles 1 unit. If a light beam is shown to several bottles, then this absorption adds up. If, for example, a light beam shines through a milk bottle and then a juice bottle, then 5 units are absorbed. If it passes through 3 empty bottles, then 3 units are absorbed. In the example given below, we have indicated the total amount of light absorbed when shining light through each of the rows and such of the columns. This is the example. To solve this puzzle, we must place a bottle with 1, 2, or 3 units of light absorption in each compartment, with the sum of the units in the first row equaling 5, in the second row 6, etc. The middle column contains 3 bottles and also absorbs 3 units of light. The only way this can be done is for each compartment of the middle column to contain one empty bottle absorbing 1 unit of light each. What about the other compartment? Unfortunately, we don't have enough information to solve this puzzle. Here are two different solutions. Cat and the radon transform. Until relatively recently, if you had something wrong with your insides, you had to be operated on to find out what it was. Any such operations carried a significant risk, especially in the case of problems with the brain. However, this is no longer the case as we described in the introduction. Doctors are able to use a whole variety of scanning techniques to look inside you in a completely safe way. A modern computerized axial tomography (CAT) scanner is illustrated on the left. This is the scanner. In this scanner, the patient lies on a bed and passes through the hole in the middle of the device. This hole contains an X-ray source which rotates around the patient. The X-rays from this source passes through the patient and are detected on the other side. The level of the intensity of the X-ray can be measured accurately and the results processed. The resulting fan of X-rays is illustrated in the following figure. This is the particular figure. As an X-ray passes through a patient, it is atten- attenuated so that its intensity is reduced. The degree to which this happens depends upon the material the ray passes through. Its intensity is reduced more when passing through bone than when passing through muscle, an internal organ, or a tumor. A key step is reconstructing an image of the body from a set of X-ray measurements is to carefully measure exactly how different materials absorb X-rays. When an X-ray passes through a body, it does so in a straight line, and its total absorption is a combination of the amounts to which it is absorbed by the different materials that it passes through. To see how this happens, we need to use a little calculus. Imagine that the X-ray moves along a straight line and at a distance s into the body. It has intensity is. As s increases, intensity s decreases into the body. It has an intensity delta s. Its intensity is reduced by a small amount of delta I. This reduction depends both on the intensity of the X-ray and the optical density US of the material. Provided the distance travel is small enough, the reduction in intensity is related to the optical density by the formula delta I equal to minus U of S into I of S delta S. Now when the X-ray enters that the body, it will have intensity I start, and when it leaves, it will have intensity I finish. We can combine all of the contributions to the reduction in the intensity of the X-ray given by all of the parts of the body that it travels through. Doing this, we find that the attenuation, the reduction in the intensity is given by I finish equal to I start into e power minus r equal to integration u as differentiation of s. This is attenuation of one X-ray, and it gives some information about the body. Below we see an object irradiated by several X-rays with the intensity of the rays measured on a detector. Here some X-rays passes through all of the object and are strongly absorbed so that their intensity recorded at the center of the detector is low, while others passes through less of the object and are less strongly absorbed. Effectively, the object casts a shadow of the X-ray, and from this we can work out its basic dimensions. We illustrate this below. It is the X-ray source object and a detector. It is measured as X. The intensity of X-ray, where it's the detector depends on the width of object and the length of the path traveled both through the object and the aid. It is the graph of the X-ray. The graph shows the intensity of the rays as they hit the detector. Rays that travel through the full width of the object have lowest intensity, as we can see from the dip in the middle of the graph. Rays that just miss the body have the highest intensity. Because of all rays that are not absorbed, they travel the shortest distance. This is reflected by the two spikes of the graph. Towards the edges, the graph falls off, reflecting the fact that the corresponding rays have traveled a comparatively long distance. However, The secret to computerized axial tomography is to find out much more about the nature of the object than just its dimensions by looking at the attenuation of as many X-rays as possible. To do this, we need to think of number of X-rays at different angles theta and distance rho from the center of the object. A typically such X-ray is illustrated below. Rho distance from the object center and theta is angle of the X-ray source. X-ray detector. This is the angle of the X-ray. Theta. Rho distance from the object center. It is an object. The X-ray will pass through a series of points x, y at which the optical density is u, x, y. Using the equation for a straight line, these points are given by x comma y equal to rho cos theta minus s sin theta comma rho sin theta plus s cos sin theta x s cos theta, where s is the distance along the x-ray. In this case, we now have I finish equal to I start into e power minus r rho comma theta, where rho comma r into rho comma theta equal to integral u rho cos theta minus s sin theta comma rho sin theta plus s cos theta differentiation of s. The key point to note in these two images is that the four straight lines making up the sides of the square show up as points of high intensity arrowed in the radon transform. The arrowed points give both the orientation of the lines and their distance from the center of the square. The reasons that lines give large the, re- the reason that lines give large values for r at certain points is that an X-ray passing straight through a line is strongly absorbed, whereas one which misses it evenly slightly is hardly absorbed at all. Tomography has many applications quite different from those in medicine. An interesting example comes from archaeology, where tomography was used to determine the cause of Tutankhamun's death. A CAT scan of the mummy revealed a swelling in the knee, indicating that that was the result of a massive infection. The cause of this was probably an injury inflicted by a fall. Whether Tutankhamun was pushed or fell by accident, however, will have to remain a mystery which even a CAT scanner cannot solve. Emission tomography has many examples like tomography, GPS, and how to land an aircraft safely, detecting landmines. Thank you for giving this opportunity.